Superposition is the next big idea we need to get our heads around. To explain how it works, I'm going to start by posing a question. What happens when two waves in the same medium meet each other? We know what goes on when one wave reflects, refracts, or diffracts, but how about two waves colliding? The answer is easiest to see with waves on strings. We can take a string and send pulses down it. A pulse is a really short wave, like a single bump that goes down the string. If we make two pulses and send them in opposite directions, they will meet in the middle and superimpose. But what does this actually mean? It's time to have a close look. Here's a hypothetical string, and look, it has two pulses going down it. They are the humps you can see, and they're both moving toward the center of the screen. Try and predict what will happen when they bump into each other. Here we go. Whoa, that's weird. The two waves made one big wave. Here's what happened. The two pulses had the same amplitude originally. They were both the same height above the string. When they collided, the pulses actually combined into one, and their amplitudes added together to make a pulse with a double amplitude. Remarkable! What's more, the original pulses are still there. If we go ahead in time, they'll split apart again. In physics, we call this constructive interference. Construction is building and constructive means adding. This happens when the crest of one wave meets the crest of another, or the trough of one meets the trough of another. Another way to say this is that the two waves are in phase. As a result, their amplitudes add up to make a wave of larger amplitude. Now let's do something really funky. Take one of the original pulses and turn it upside down. The pulse shown on the right has been inverted. You could say it has a negative height. So what happens in this case? Do we still get superposition? We sure do. This time the pulses are exactly opposite. They have the same amplitude, but one can be considered a crest and the other a trough. Therefore, they cancel out and leave nothing but a flat line. And yet, the individual pulses are still there. They move apart again and keep traveling along the string, like nothing ever happened. This is destructive interference, where instead of the amplitudes adding up, they subtract or cancel out completely. The crest of one wave coincides with the trough from another. The two waves are out of phase. What may we conclude from all this? First, it turns out that pulses moving along a string will pass through each other rather than crash. As they pass through each other, the pulses undergo superposition. Their amplitudes are combined and they make a resultant wave. When the amplitudes add together, we get constructive interference. When one amplitude is subtracted from the other, we get destructive interference. This is known as the principle of superposition, and it's very important in modern physics. You will need it to understand the last part of this paper, the topic of wave interference. I've shown you realistic pulses that look like sine curves, but it's often easier to represent them as blocks like this. In the following questions, you'll be asked to predict the resultant waves formed by shapes like this, moving in opposite directions. You are close to the end of 2.3 waves. Thanks for watching.